Hello and welcome. Today is Monday, April 13th, and today we'll be doing Flippy entry number 7 and take some questions from Mastering Physics as well. How you guys doing today? We have a few people already up and running. Even though spring break is over, I'm glad you're able to wake up. Chapito's here, of course. I really don't know how I woke up. Well, we're glad you did, so we can get started. Let's see. There we go. And I forgot to put everything on charge, so I'm charging right now. We're at 52%. Okay, not bad. I'll have to charge it while doing stuff. All right. Now, if you haven't read on our Canvas, we're going to go ahead and cancel our shoebox project. Shoebox project has been canceled. Yeah, we're not really sure if we're going to have the time to do all that stuff, and our trajectory, our planned time to return may even change. So everything is pretty uncertain right now. Therefore, we're going to go ahead and cancel the cancel the shoebox project. Man, I wanted to get the test. I know, right? Yeah. So for the most part, we'll start cutting things out from our curriculum. Cutting as in making it more streamlined. We're only going to do the things that we can online, and then some of the other stuff we're just going to have to put away, unfortunately. So it'll be, in one way you can think of it as less work, but it is different type of work. Unfortunately, we're not going to be able to do all the things we had planned, like the kickball game and all that stuff. So all that stuff that we have planned for at school has been canceled. Our focus will shift towards mastering physics. That's how you'll get most of your points, because that's online, and that's the only way I can grade stuff. But yeah, and we'll have like a quiz or something later this week. I think is it Thursday? Do you guys know? Someone, you can check on your calendar. I believe it's Thursday. You'll have a quiz on circuits. All right. Let's see. On a different note, if you guys have used the Microsoft Teams chat feature, oops. So Teams.Microsoft. So I'm going to write it down. Teams. Teams.Microsoft.com, and you should log in with your school account. There we go. Let me switch the screen. There it is. So, or I think there's an app too. It says stay in the know, turn on desktop notification. No, get away. Alright, so all of your classes will be here, right? This is your Microsoft Teams stuff. And here on the top left, there's a chat. And, oops. Read, whatever. See when your messages are read and sent. Oh, others got it. Blah, blah, blah. Oh, look, I'm testing it out with Garrett. But you can use this chat feature and send me a message, but only for like very critical. Like I'm getting too many emails, so we're trying to split it up. I'll be on Microsoft Teams from 2:15 to 3:15, so basically 6th period. So I can take critical questions that you may have around that time. Okay, have your questions ready, and then just type the question only. Keep it streamlined in there. All right. So that's the chat feature. You just go to teams.microsoft.com and then click the chat button on the top left. Yeah. Chapito, you want to test it out for us? If you can, go ahead and do it so I know it works. Wait, what were the teams? Oh, okay. It is 2:15 to 3:15 p.m. Ah, Christian Tran, this is a test. There you go. Thank you, Christian Tran. Thanks. All right, so 2:15 to 3:15. Go ahead and if you have questions, you can type there, and I'll answer. All right. Yeah, I'm getting like 100 emails a day, and there's no way I can get through all of them. It's just piling on and on, never ending. Kind of overwhelmed right now trying to figure out what I'm going to do with all my classes. All right, anyway, let us begin. Flippy number 7. Flippy number 7. And as you may have noticed, this is the last Flippy entry. We're done. Wow. 2 months. This was a 2-month project, right? What's the title? The title is Electric Power. Electric Power. And so remember, you have electric charge, force, electric field, electric potential. So electric charge, electric force, electric field, electric potential, and then capacitance, current and resistance, and now electric power. All right, so we'll start with the top. Let's have some circuits. So here's our simple circuit. We know that the big line and the small line here, this is the symbol for chat. What symbol is this? Can someone tell us if you reviewed on Friday like you were supposed to, so that you didn't lose everything over spring break? What's this thing here? Big line, small line. This is a symbol for battery. Very good. This is the battery. The small line is the negative. The big one is the positive. We'll go and put a delta V here. Delta V tells you the voltage of the battery. The squiggly thing, the zigzaggy thing, I didn't really draw it very well. Let's try again. There we go. The zigzaggy thing is a resistor R, and we know that the current flows from the positive end to the negative end of the battery. All right. So in this circuit, it's a nice clockwise direction. We have 3 circuits to draw here. Okay. The next one, we'll put 2 resistors with our battery. one up here, one down here. Try to make your circuits nice and neat. Right. When you have two resistors back to back, these resistors are blank. The word starts with an S. Are blank resistors. Blank. What is blank? When you only have one pathway for the current to travel, they are in series. All right, Christian Tran. Okay, so here's our series. And of course the other one is parallel. For parallel, you have more than one pathway. Alright, so of course we're trying to get from one side of the battery to the other. Here's the plus, here's the minus. The current will come out and then get to this fork on the road, and when you get to this fork actually has a term, a name, right? It starts with a J. What is this called? This point. So when you're about to split off into two different pathways, like so, we call this a junction. And so when you hit this junction, you have a choice. You can go through resistor 1 or resistor 2. Oh, I should have put little subscripts here. Resistor 1, resistor 2. There we go. And of course, if they're the same resistance, if they're both equal, then it will split up 50-50, 50% to the left, 50% to the right. If they're not equal, then the smaller one will get more current and the bigger one will get less current. But you can only take one pathway at a time, so any individual charge can only take one route at a time. So if it chooses to go through resistor 1, it'll get to the bottom and meet up at this other junction here at the bottom. If it went through resistor 2, it'll come back and meet up here at the same junction. So you can only take one set of staircases at a time. And once you're there, you're now at the bottom of the battery, so you're done. Alright, let's talk about power now. Power. The simple equation was that power is equal to, this is capital P by the way, not lowercase p. Lowercase p was momentum. Power is equal to I times V, current times voltage. Alright, but we also had other equations. We were able to substitute in Ohm's law to get the other ones. So power is also equal to I squared R, and it's also equal to V squared divided by R. I'll write it as a fraction. Like that. I squared R or V squared over R. If I want the total power, P total, I can always add them up. Or, oops. Or I could use the total current in the system, I total, and multiply by the total voltage in the system, V total. Okay. And these rules apply to both series and parallel. So power just adds up scalarly, linearly. Doesn't matter what kind of system you have, even if it's like complex. If it's a combination of both series and parallel, it just adds up. So the more light bulbs and stuff that you have in your circuit, the more things that you have hooked up into your outlet, the more power you're using. Okay, remember, power is energy per second, so the more energy you're burning every second. Okay, so a typical like a computer, right, has a power supply of somewhere around 400 to 500. If you have a gaming PC, it might be even higher, 650. If you're using SLI with like dual GPUs, it might go up to 1000. So 1 kilowatt. All right. So you can use P total equals I tot V tot for any circuit. All right. Now let's go to the bottom side. Let's see. For current, batteries maintain a constant delta V. Ooh, my V is all weird. Delta V, and then batteries cannot convert energy. Right? It's your circuit elements, the resistors and all the other stuff that you add into your circuit, that will take your energy, convert your electrical potential energy into other things like heat and light. Generators convert mechanical energy into electrical energy. So generators do the opposite of what motors do. Right? All of your electrical components that use electrical energy and produce some sort of mechanical or thermal, generators do the opposite. They convert mechanical energy. Oh my gosh. I didn't charge my pen. Mechanical energy to electrical energy. current can be AC or DC. Uh, AC is alternating current. And it changes, it oscillates, it goes back and forth. Oops. Like a sine graph. Yeah. It's actually sine, or S-I-N-E, not sine. So sin, or sine, is short for sine, S-I-N-E. And then DC, or direct current, flow of current is always the same. Yeah. So it's sine, or sorry, with alternating current AC. That's the stuff you get out of the walls. It comes and goes, meaning it oscillates back and forth like a sine wave. There's a high and a low. High means it's coming in, low means it's going back. Whereas direct current, which you get from direct voltages or constant voltages like a battery, so battery only gives you current in one direction. There is no going backwards. It just flows in one direction from the plus side to the minus side. Standard household power outlet. Standard household power outlet. (110 to 120 volts). So in America, we get somewhere around 120 to 110 to 120 volts. It is AC alternating at 60 hertz. Okay, so what we get out of the walls is power or electricity. Basically, it comes in at somewhere in the 120 volt area. Okay, it is alternating, meaning it comes and goes 60 times a second, 60 hertz. So if we're using traditional light bulbs, the light bulbs are basically going on and off 60 times a second. As the moment it's at some point the current on its return trip will hit 0 volts. So there is a moment when the light bulb is actually not on. So it's on and off like 60 times a second. Circuit and eventually we'll talk about LEDs and how they're different from traditional light bulbs. We'll look at how to actually set up LEDs. I made some like a simple LED shelf light thing. So I think LEDs are like the I guess everyone's doing it. It's like the next big. It's not. Shouldn't say it's big, but it's like everyone's putting up LEDs on their desks and behind their TVs and behind their I don't know, TV stands, trying to light up their house with RPG lighting. So we'll take a look at how to set up LEDs ourselves and talk about how it works later on. Circuit elements like resistors, light bulbs, and diodes. So diodes are what we call LEDs, light emitting diodes, which and they are unidirectional, meaning it can only work if current flows in one direction. If it tries to go backwards, it stops. Consume energy, turning it into heat and light. Oops. Turning it into heat and light. Okay. So of course resistors are the ones that are making most of the heat. Light bulbs do get hot, especially traditional ones, because they're not very efficient, and so it does give you some heat. And the rest, because the little filament gets so hot that it starts to glow and gives you light. Electric power. So to measure how much energy they're burning per second, we have electric power. Capital P. And it's equal to energy per time which is I times delta V, the battery. Now if you want individual power, of course use the individual voltage drop and the individual currents, as you did in lab number 2. By the way, lab number 2 is due this Saturday, and we will go over the lab tomorrow, according to our calendar. Units is watt, 1 watt, 1 W is equal to 1 joule per second. And based on this equation, we can see how it's also equal to 1 amp volt AV. Okay. And you should also remember what current is. Remember, current I is coulombs per second, so charge per second. Charge per time, I should say. So coulombs per second times voltage is a watt. Is what? It's a watt. Alright, so at the top you should have electric power as your title. That's the little tab at the bottom, actually. The top side has all of these pictures with the power equations. Remember, you can use any of these power equations for any circuit, so it doesn't matter what kind of circuit you have. The new vocab term is junction. Junction, what's your function? Well, it's to split up current and or recombine it again. And then on the bottom side you have all of this content and information. So that's Flippy number 7. That's the end of Flippy's. Put it all together. Go ahead and color and decorate the front cover so it's nice. We will submit those Flippies one way or another. If school returns, then we'll hand it in by ourselves in person. If school does not return, then we'll have to take pictures one at a time and upload it to Canvas if school is canceled for the rest of the year. Not really sure if that's going to happen. Alright, so let's just touch up on a few things like junctions. So what do junctions do? Some extra notes here. Well, if I have a point, right, we know that whatever goes into a junction has to equal what comes out of a junction. So let's say that this point is a junction and I have 5 amps of current going into this dot. So this dot can represent any of these. So imagine this dot representing the junction here. Oops. There we go. Get rid of that. So into this dot goes in 5 amps of current. That means it's 5 coulombs every second. And do we put in the Flippy or into Flippy? I just said Flippy. Flippy, put it in your Flippy, make it colorful, make it designed. If school returns, you turn it in by hand. If school does not, you take pictures of it and upload onto Canvas. These are extra notes, so this is not Flippy. Not Flippy. Regular notes. All right, thank you for asking. So 5 goes in, and you know one of the branches is taking 2 amps of current. Then of course the remainder, the one that is going to the right, has to be whatever's left over. So 5 minus 2 is 3 amps. Okay, this is conservation of charge. Okay. Meaning current into a junction equals current out of a junction. Do we have a follower? Hey, we have a new follower. Alright, so current into a junction equals current out of a junction. What is the title of the entire Flippy? Well, electricity or electrostatics and circuits. I'll type it. Electrostatics and circuits. Or you could just call it, like the main title could be electricity. You made a new account. Did you forget your old one? Okay, so these are junctions, and it's just basically adding and subtracting. So just take a look at the arrows and what's going in, and then you can figure out what's coming out of the junction. Alright, what else? Oh, let's take a look at mastering physics, shall we? Mastering physics. Where is it? There it is. Our next assignment is due, I don't know, when is it due? Is it Saturday? Oops, wrong class. Here we are. Honors Physics. It is due on the 18th, yep. All right, we'll do a couple, and then we'll call it a day. Ah. Okay. Question number 1. Whoa. Mastering physics. Number 1. Dependence of resistance on resistor dimension ranking task. All right. Oops. Continue. For what? I couldn't log in on my phone. We'll do a couple every day, Chris. So eventually we'll get through it all. All right. Rank the block based on its electrical resistance along the 3 illustrated coordinate directions X, Y, and Z. Okay. So the idea is that the resistance is equal to, well, we're going to use the resistance equation. Resistance is equal to rho times the length divided by the cross-sectional area A. Okay. Now, rho is, my rho is kind of weird. Let's try again. There we go. My rho is called the resistivity, which is the material property. It's a material property. And so different materials like copper or silver or gold will have different resistivity values. L and A are length and area. So you already have all these notes. So take a look at your notes. Reference your notes. That's why you take notes. And so all you have to do is figure out what the area is and what the length is for each axis. So for example, for the x-axis, okay, the length is equal to the length along the x-axis, and that's 3 centimeters. Okay, the cross-sectional area is the face. Okay, so on the x-axis, what is the face of the rectangle? So this rectangle looks something like this. Basically, depending on which way you send the current, you're going to get different resistance values. So this red line represents the x-axis. So we're looking at it 3D. And so the length was this thing here, L, which is 3. Okay. The area for the x-axis will be this face here. And so that area is 10 by 4, or 10 times 4, which is 40 centimeters. Okay. And so you can do this in proportion. Rho is going to be the same value for all of them, so you can just ignore it and say that the resistance is proportional to L divided by A. So L over A. Whichever gives you the biggest L over A will give you the biggest resistance. So 0.03 divided by 0.4 for the first one. For the y-axis, let's go and use blue. Okay, the y-axis is shown as this one here. Yeah, it looks weird. The y-axis is right, the x-axis is coming out, the z-axis is up and down. But you just follow the model. Don't harp on it too much. So the face on the y-axis is the right face here. The length would be from here to here for the y-axis, which is equal to 10 centimeters. Okay, the face along the y-axis, the cross-sectional area, is 3 by 4, so that's 12. This height here is 4. So 3 times 4 gives you the 12. Alright, so 0.1 divided by 0.12, or 10 divided by 12, is your ratio. So let's go ahead and use a different color. Green. Green will be the z-axis, and the z-axis is up and down in this picture. And so we're going to use this face here. The length is 4 centimeters. And the area would be 3 by 10, or 30. Why is it that side and not the smaller one on the right? Kuya Casey. Oh, wait, never mind. I got it. Okay. We're looking at the cross-sectional area along the axis. So along the z-axis, this is the z-axis. Along the z-axis, it'll be the top side of your box. So that's 3 by 10, which is 30 centimeters. Okay, so for all of these, we're going to just take the fraction. So we're going to ignore the row, because row, the material property, is the same for all 3 of them. Wait, I thought it was 9, 10, 10, 11. Sword Hero, what are you doing? Go away, Sword Hero. This is honors physics. No, we've never changed our stream time. You can scroll down below and check our stream time. Can you see it on our page? Alright, let's go and take the fractions. So fraction of L, so that's 3 over 40, or 0.03 over 0.4. Doesn't matter which one you use, because the units will cancel. So this one is 3 over 40, this one is 10 over 12, and this one is 4 over 30. Okay, so obviously, now you can rank them. Right, so this one, and then this one, and then this one. All right. Hey, Sword Hero, be nice. Ban / ban Sword Hero 1. There you go. Just because you don't know people doesn't mean you can treat them poorly. You should always treat everyone as if you're seeing them, in person. This is one of the things that I think is very important to learn. It's the idea that just because you're online doesn't mean you're anonymous and you can be a jerk and whatnot. You represent yourself no matter where you are, no matter what platform you're using. So propagate goodness in the universe. Sword Hero is from a different class. It's not even in honors physics. All right. That was number 1. If the dimension of the block double, okay. So you can do the same thing again for the second part. So I'll let you try that on your own. How many questions are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 23 questions. Yikes. We gotta do like 4 of them. Alright, number 2. Numero dos. Mastering Physics number 2. A potential difference of 18 volts is applied to a resistor whose resistance is 220 ohms. What is the current that flows through? This is just using Ohm's law. That's pretty simple. Remember, Ohm's law is V equals IR, Vir. So if I want current is just V over R. Yay, done. So you should be able to do all this stuff by Thursday when you take your test. Quiz. Quiz on Thursday. Number 3. Let's take a look at number 3. What voltage is required to produce a current through a resistor? Blah, blah, blah. Another Ohm's law question. Yay. So measuring physics numero 3. V equals IR. And now it's just plug and chug. Multiply the two numbers. Yay. So now you might have different numbers, so make sure you plug in your own numbers. Number 4. Yeah. A battery with an EMF. EMF is another way of saying voltage. Mastering physics number 4. EMF. EMF is called the electromotive force. It's not really a force. So, not a force. It's just the voltage. There's a little bit more to it. If you'd like to learn more, consider taking AP Physics C. But, we can just say that it's the voltage of a perfect battery, an ideal battery. It is not a force at all, even though it's in the name. Alright, a battery with an EMF of 1.5 volt delivers a current of 0.44 amps to a flashlight bulb. How long must the flashlight battery operate to do 150 joules of work? Alright. So we have to combine our power equation and figure out time. So power, remember, is equal to work per time, or energy per time, right? Power is equal to work or energy divided by time. So that's a general formula. Remember how we did power in mechanics. So if you have like a car engine, it does power. Well, you can do change in kinetic energy divided by time. That's the power of your car engine. Okay. So if I want time, so P is equal to time, not power. So time must be equal to work or energy. I'll say energy here. Energy divided by power. Energy divided by power. Yeah, this fraction thing, you can always put like a 1 here down below and cross multiply. We always have students mess up the isolation of variables here, right? So just if you ever have like a fraction on one side and a just a single variable on one side, put a 1 underneath, 1, and then cross multiply. So you can see power times time equals work. So power times time equals work or energy, whatever, and then divide both sides by time, and this gives you, divide both sides by power, not time. I want time by itself. Divided by power, and this gives us time by itself. So time is equal to energy over power. So I guess that's it. We know how to get power. If I have voltage and amp, so power is also equal to current times voltage, right? So multiply the two numbers to get your power, and then energy divided by the power gives you your time. All right. 5 series in parallel resistors. I'm going to skip 5. 5 is pretty self-explanatory. Oh wait, no it's not. There's some crazy stuff going on in number 5. We'll get to it. And then there's 6. Oh, 6. Christian Tran wanted 6. We'll finish with 6, I guess. So it says a 210 ohm resistor has a potential difference of 7.7 and is connected in parallel with a 130 ohm resistor. What is the current supplied by the battery to which the resistors are connected? Current is, this is Maastricht Physics, number 6. Using Ohm's law, we can see how current total is equal to V total over Req. Right. So we know that the two resistors are in parallel. So what is the resistance of 210 and 130? Anytime you have resistors in parallel, the total resistance is going to drop. Let's take a look. Here's the general formula, Q for resistors in parallel. Remember, it's the inverse of inverses added up. 1 over rec is equal to the sum of inverses, but then to find rec by itself, you have to take the inverse again. So 1 over 1 over 1 over. There is a shortcut though. If you have two resistors in parallel, what's the shortcut method? Anyone know? Z1NC, you're new in here. Do you know the shortcut? Well, the shortcut is product over sum. Product over sum. Okay. Make sure you use parentheses around your denominator if you're doing this on a calculator. Otherwise, you might get some weird answers. Or you could add the reciprocals and then take it to the -1 power. So taking it to the -1 power is the same. So if you like that, that also works. So this is equal to 1 over 210 plus 1 over 130 to the -1 power. Yeah. So let me see if I can do this. 210 product over sum also works for resistors in two resistors in parallel. So that's 340. Oops. 80.3-ish. And then just voltage divided by resistance. What is V total? Well, V total is going to be equal to any of the voltages, so it's given. And voltages are equal because they are in parallel. So take a look at your parallel notes. So if you know that they are parallel, then the voltages must be the same. And so voltage divided by the total resistance. All right, you got that, Christian Tran? I think that's it for today. Thank you for tuning in. I'll see you next time.